Hello, my name is Christopher Robert Stum, and this is the third in a series of 3 videos dedicated to explaining a process known as completing a square. In the second video, I explained the actual process, that is, what we do to complete the square. So in this third video, I'll be explaining various applications of that process. I will more specifically be focusing on 2 specific applications, the first of which being solving for values of x for a given polynomial degree 2, that is a given quadratic formula. The second of which being plotting parabolas, that is the graph of a quadratic formula. So let's begin with the first. So suppose, and I'm just going to first give us the reminder of what we define algebraically as a perfect square, the form x plus b divided by 2a squared equal to x squared plus b over a x plus b divided by 2a squared. And now, when we talk about solving for values of x, what we're implying is that we're given a quadratic formula of the form y equal to a x squared plus bx plus c. And we're given that y is equal to some value. Whatever value we may choose, could be at 1, 2, 3, or even 0, need not matter. But when we solve for a value of x, we're saying given y, find the x which would produce it. So it's almost like we're working backwards. Rather than starting at saying given x, find y, we're saying given y, find x. So that's kind of one way to interpret what this means. Although we're not necessarily restricted to doing it in this manner, we're going to assume the value of y to be 0. And there's a very good reason for which we're going to do that. Because this would denote an x-intercept. Because geometrically speaking, we would observe that if we have our graph of y and x, as shown here, if we were to plot a parabola such as the one given here, where this is the graph of y equal to x squared, this point here has the coordinates x, and obviously this x is 0 since it's at the origin, but it could be somewhere else. But in any case, it's x 0, such that if we moved it over, it might be x 0, x 0. But the point to really emphasize is that the y coordinate is 0, and so the x-intercept of this parabola is identified when y is equal to 0. And so that's what we're going to pay careful attention to. We observed that there are 3 primary occurrences that we can encounter when dealing with quadratic formulae regarding the number of x-intercepts we might solve for. The first of which being here, where we have 1 x-intercept, right? The second of which, so suppose now that I had this parabola, for example, which could open upward or downward, but in any case, it has now 2 x-intercepts, such that here we have the point x 0, and so this is the opposite of x 0. And note that this might not necessarily be centered about the y-axis. It may be deviated over again, but here we have 2 x-intercepts, and so that's being denoted by the fact that if we solved for the value of x, we would have plus or minus, that is, we would have the opposite of whatever value we would determine for x here. And so that's the second case. So we observe there's a third case, and that third case would entail where suppose we have the same plot x, y, so here's our y and x, and we have a parabola such as this. Either, again, if it was open downward, it'd be facing this way, but in this case we observe, since it's not really, there's no point touching the x-axis, there are no x-intercepts to be found. So we see that we could have 0, 1, or 2 x-intercepts. And so we have those 3 different types of scenarios we can encounter. Now, when we're talking about solving for those values, the process by which we would do this, that is either using the first method or the second method discussed in video 2 for completing a square, isn't really that important. But for the sake of simplicity, I'm just going to prefer and insist upon using the second method, that is the one entailing working both sides of the equation. And I'm going to start by giving us an example in which we actually define a, b, and c, that is these arbitrary constants, to be some numerical value, such that it just makes it something that's actually real and tangible in a way, because sometimes people are less comfortable dealing with variables, as it were. So let's suppose that we're given the graph y equal to 2x squared plus 6x minus 4, where c defines the opposite of 4. And so we want to solve for, again, where y is 0, such that we can define that as the x-intercept. So first thing that I would probably observe is, again, the goal is the same. We want to transform this side of the equation or this variant into something of this form such that we can substitute this in place of it. but we're going to work both sides of the equation. In doing so, the first step I would say is we need to identify which is the lead coefficient, which here we see is 2, and so I would actually make note of that. I'd say that A is equal to 2, and so B in turn is equal to 6, and so C is equal to the opposite of 4. We factor in the sign here because we observe that this is really analogous to adding the opposite of 4, and so that's plus C. And now we observe that the first step entails dividing both sides of the equation by 2, such that 0 divided by 2 is 0, so we end up with by properties of fractions, we can expand this such that we have 2 over 2, x squared. Cancellation of 2's, such that we just have x squared, plus 6 divided by 2 is 3, so 3x, and that's going to be a minus 2. And so the next step would entail subtracting c over a from both sides of the equation. Notice here that c over a is defined as negative, so that is to say, by subtracting it, that is the opposite. So it's the opposite of the opposite, that is subtracting double negatives results of positive, so to cancel the negative 2, we add 2. And so here we observe that we would add 2 to both sides of the equation. And so now, the last step in completing a square entails adding b over 2a squared. So we would add plus b over 2a squared. And so first we need to determine the value of b over 2a. So consider that b is equal to 6, so this would be 6. 2 times a analogous to 2. 2 times 2 is 4. And 6/4 does simplify to 3/2. And so now, the property of exponents, we can distribute the square inside the parentheses to each term, such that we have 3 squared divided by 2 squared. And observe that 3 squared is 9 and 2 squared is 4. And so we are adding 9/4 to both sides of the equation, so 9/4. This is now in the form of a perfect square. And so by this definition, we can now substitute it for this, such that we have 9/4 plus 2 is now equal to x plus, we determine b over 2a to be equal to 3/2 squared. And so now we see that this substitution has now been made. And notice that this has afforded us a pretty important advantage in that here we have an x squared and an x. And so it makes for ambiguity in solving for what the value of x might actually be. Whereas once we make the substitution, we've only one x to deal with and all the rest are constants. So now we're in a position to solve for x. So it just so happens that although completing a square isn't necessarily, not the only purpose of completing a square, that is, its only purpose is not simply to solve for x-intercepts. It just so happens that it makes for great practicality to do just that. And so in that way, it's useful. So here, let's just simplify this such that we can express it in terms of a single rational expression. So we observe that in order to add, we need like denominators, so we can multiply this 2 by 4 over 4, such that we preserve the ratio but have common denominators. 2 times 4 is 8, and 9 plus 8 is 17, and so this becomes 17/4. And so we have 17/4. And now we want to simply solve for x, and so we want to cancel this square, and so to do that, let's just take plus or minus the square root of both sides of the equation. And doing that is a cancellation of 2 there, such that we have and I'm just going to switch these around such that we now have x plus, meaning I'm just going to reorder, so this is here, that's there, 3/2 equal to plus or minus the square root of 17 over 4. Now observe that by the property of radicals, we can separate these such that we can express them as 2 separate radicals, the square root of 17 over the square root of 4. The square 4 is a perfect square, and so we observe that this is just the square root of 17 divided by 2. And so now, to isolate and thus solve for the value of x, we simply add the opposite of 3/2 or subtract 3/2 from both sides of the equation, such that we have plus or minus the square root of 17/2 minus 3 over 2. And now that we have common terms, that is, we have a 1/2, we can factor that out, or common denominators as it were, such that now we can observe this is 1/2 times plus or minus the square root of 17 minus 3. And that gives us the x-intercepts for this particular curve. And notice that these are the values of x at these points. And since plus or minus is indicated, we would therefore know that in this particular instance, the parabola touches at some 2 points. Not necessarily, again, centered at the y-axis. It could be deviated, but this tells us those x-intercepts. So now that we've seen this specific example, I actually want to take the time to show that although this is useful, we can use the general process by which we would complete the square. That is the same process here, but instead of in a particular instance, that is, instead of just in this specific case, we could apply it to the algebraic variant, that is the general case, and from that create a formula from which, or I'm sorry, with which we can evaluate the x-intercepts for any quadratic formula of this form. So in doing so, we would derive what is referred to as the quadratic formula, the formula that can be used to determine the x-intercepts, if they exist, of any parabola. So let me now use this algebraic variant and do the same process, that is complete the square with the same second method previously used and derive that formula. So we're assuming y to be equal to some value 0, so we want the x-intercepts, and that's equal to ax squared plus bx plus c. Again, same method, so we're going to divide both sides by the lead coefficient, so that's going to be 0, because anything divided by 0 divided by anything is still 0, and so we have cancellation of the lead coefficients here, x squared plus b over a x plus c over a. And so now we observe that we want to subtract c over a, we're going to add the opposite of c over a to both sides of the equation, so the opposite of c over a is equal to x squared plus b over a x. And now, to complete the square, we add b over 2a squared to both sides, so b over 2a squared, and this in turn is b over 2a squared. This is now in the form of a perfect square, such that we can substitute this. I'm just going to put this over here and flip it, such that we have x plus b divided by 2a squared, and this is now equal to b over 2a squared minus c over a. And so here we have this. Again, we want to solve for x such that we would, to do that, take the square root of both sides, so plus or minus the square root, cancellation of the square there, thus we have x plus b divided by 2a, and this is equal to plus or minus the square root of b over 2a squared minus c over a. And lastly, we want to isolate the x such that we have x equal to the opposite of b. Again, the ordering of the terms is not important, because if we define, since we're adding the opposite, it behaves commutatively in accordance to the definition of addition. And so b over 2a, the opposite of b over 2a, plus or minus the square root of b over 2a squared minus c over a. And so here we have x expressed in terms of this, and now I just want to move up here such that I can save some room. And so I'm just going to make some simplifications. So if we're given that x is equal to the opposite of b divided by 2a plus or minus the square root of b divided by 2a squared minus c over a, we want to first combine these such that we have a singular rational expression. But before we do that, let's just distribute the square in here. So if I distribute the square, this produces a b squared. And squaring a 2 yields 4. And squaring the a yields a squared. And so this is b squared over 4a squared, and that's minus c over a. Now, in order to subtract or add, we want to observe that we need common denominators. So we observe that multiplying this by 4a over 4a is still analogous to multiplication by 1. So preserving the ratio, but changing the denominators such that we have common denominators, allows for now we can combine these and as such express them as a singular rational expression. So we can distribute the c such that we have minus 4ac. And so this numerator becomes b squared minus 4ac, and the denominator being the same is now just 4a squared. And so by the property of radicals, we can now observe that this is x equal to the opposite of b divided by 2a plus or minus the square root. We can now express these as separate radicals such that in the numerator we have b squared minus 4ac, and this is all divided by the square root of 4a squared. 4 and a squared in this particular instance are both perfect squares, and so thus they are the same as 2a. And so now we have common denominators, and as a result can express the entirety of this side of the equation as one rational expression, which I will do up here. So combining these together, we see a numerator of the opposite of b plus or minus the square root of b squared minus 4ac, and then this is all divided by the common denominator 2a. And that is the quadratic formula, the formula with which we can discern the x-intercept of this formula. So let's do that now. So we're given this, and so we want to, using this, x should be equal to, the value of b is 6, and so this will be the opposite of 6, plus or minus the square root of 6 squared, because that's b squared, minus 4 times a is equal to 2, so 2, and then c is the opposite of 4. So, and this is all divided by 2a, so 2 times a equal to 2. So now we just simplify and we should have the exact answer. So x equal to the opposite of 6 plus or minus the square root. 6 squared is 36, and subtraction, here we have a minus 4, but we could also interpret this as the opposite, so we could write it as plus the opposite of 4. And as such, we observe that the opposite of 4 times the opposite of 4 is a positive 16, and 16 times 2 is 36. So this is 36 plus, I'm sorry, 16 times 2 is 32, and this is 36 plus 32. 36 plus 32 is 68, so this simplifies to 68. And now we observe 68 is actually equal to 17 times 4. 4 is a perfect square, so we can take that and by properties of radicals observe that this is actually equal to 2 and the square root of 17. And so the denominator simplifies to 4, 2 times 2. We can factor out a 2 from the numerator here such that we have x equal to 2 times, and I'm just going to reorder the terms again. This will be plus or minus the square root of 17 minus 3, and thus over 4. We have a simplification here such that this is 2, and we can factor out the 1/2, so x is equal to 1/2 times plus or minus the square root of 17 minus 3, and that is the same as what we had before. So we see the advantage of the quadratic formula is that it allows us to solve for the values, that is the x-intercepts, without having to first complete the square. So that is the advantage it kind of provides us. Now, there's more to the quadratic formula than what I've shown you, but I'm going to discuss it in another video. So we're not going to delve any farther into the quadratic formula because this video is strictly dedicated to applications of the perfect square. It's simply worth noting that that is one method by which you can derive this formula. Alright, so now let's discuss the second application of completing a square, which is more of a graphical approach, which is to plot parabolas. Before I actually delve into the specifics of what that entails, I want to provide a geometric analog of what you might interpret a parabola to be. And to do that, I want you to consider a definition. That is, if a graph is analogous to a set of points corresponding to the solutions for a given equation, then let's define a parabola as the set of all points x, y to be the points equidistant from some point, so some point, and I'll actually put this here, and some line. So some distance, such as the one I've drawn here, and some line equal to a constant, such that it's, so here, I'll just draw our line. And there's that point. And we'll define, again, this is the point to which we are referencing. A point equidistant, this distance being the same as this distance from some line and a point. So this is the same distance from that as it is from that. And a parabola being the set of all those points of equidistance. What this would entail is that what would determine the distance of this point from this point would be quite simple. If all of the points are defined as equidistant, then observe that the center, that is the vertex here, and would be some distance p and p, because again they have to be equidistant, so it has to be the same distance from this point as from that line. And this is the vertex. So this is the vertex, this would be the focus of the parabola, and this is referred to as the directrix. And so since it's equidistant from each point, anything on this side would necessitate that we have some point here, here, and so our parabola now takes the form. And so there we have our parabola. Not necessarily drawn to scale, but so here we have our vertex, and thus the parabola is the set of all points equidistant from some point and some line. Now, the vertex is denoted as having coordinates h, k. And this is where the second method, that is the, I'm sorry, the first method, that is the method by which we complete a square entailing working only one side of the equation, is particularly useful. Because for example, if we start with y equal to ax squared plus bx plus c, well, if we arrange it into the form y equal to a times x minus h squared plus some constant k, the purpose of knowing h and k is that we can now discern the placement of the vertex of the said parabola. If we can discern the placement of the vertex of the parabola, we can then locate where it might be on a graph and thus determine how it looks, and thus the dimensions of all of the other corresponding facets of that parabola as well. So this would be the second application. So I want to use the previous example worked and show that by transforming it into a variant of this using the first method, whereby we work one side of an equation, we can then plot that equation. So again, given something of the form y equal to 2x squared plus 6x minus 4, we want to work one side of the equation, and so to do that we again factor out a 2 such that we have x squared plus 3x minus 2. And so now y is equal to 2 times, we want to add and subtract b over 2a squared inside, and so that's, as previously denoted, 9/4, and so that's x squared plus 3x plus 9/4 minus 9/4 minus 2. And so this is now in the form of a perfect square. Y is equal to 2 times, and I'm actually going to use different parentheses to distinguish this from these, plus, so b over 2a we determined to be 3/2, so x plus 3/2 squared, and this is minus 9/4 minus 2. And so now we simply want to combine these to a singular rational expression. So y is equal to 2 times x plus 3/2 squared. Observing that we want a singular rational expression, we need a common denominator, so we multiply by 4 over 4, analogous to when preserving the ratio, changing the denominator. So 2 times 4 is 8, and this is the opposite of 8, so we combine like terms, the opposite of the opposite, so this is the opposite of 17, and that's divided by 4. And so now we can redistribute the 2 such that we have y equal to 2 times x plus 3/2 squared, and this is a minus 17, because there's a cancellation of one of the 2's here, so minus 17 over 2. And this is now in the form of y times a, y equal to a times x minus h squared plus k, as we now see. And so this means that this is the h and this is the k of the vertex. So on our graph, if we were to draw one over here, we see that h, this being positive, denotes that we've moved this direction, and so we've moved left 3/2, which is about 1.5, and since k is negative, we've moved downward 8.5. So on this graph, we've gone down 8.5, over about 1.5, so here's our vertex, and so our parabola will look something like this. And again, as shown, we also have 2 intercepts somewhere, and so with this, we can determine the placement of that parabola. And so that entails the second method. That is the second application of the method of completing a square. Okay, so now that we've discussed these various methods, I want to make note of the fact that there are other applications of completing a square. The most notable of which entail the utility of completing a square as it pertains to solving integrals, as well as Laplace transforms. Neither of these techniques will be discussed in this video, as they entail the utility of calculus, and so they'll be discussed in a later video. I hope that these videos have been informative and helpful, and I thank you all for your time and attention.